These are notes on nuclear reactions. So nuclear reactions are any reactions that take place in the nuclei of atoms, so having to do with the protons and neutrons. Different from chemical or physical changes in which the actual atom itself stays pretty much intact. So there's two different kinds of nuclear reactions, and they're spread kind of throughout your book. The first type is radioactivity, and that's particles within the nuclei of atoms changing, which then changes the element. So we talked about how, if you change the number of protons, you would get a new element, and people always say, well, can you actually change the number of protons? And yes, you can, especially if the element is radioactive, and in fact, the element will do that itself. It will change its number of protons if it's radioactive, and we'll talk a little bit about what it means to be radioactive and why elements might do that. And that's going to be in your book, Chapter 19, Section 1, and then we're looking at 19.3 through 19.6. And then the second type of nuclear reactions are fission and fusion, which most of us have heard of. So fission is the splitting of entire nuclei, and fusion is the combining of entire nuclei into one. Fusion means to kind of put together. So that's Chapter 20, and it's Sections 1, 3, and 4 are the main ones that we're going to focus on in this course. So first we're going to look at radioactivity. And radioactivity, or elements are radioactive because their nuclei are unstable. So if you remember when we talk about the nucleus of an atom, there are often different isotopes, meaning elements that have the same number of protons, so they're the same element, but different numbers of neutrons. And what those different numbers of neutrons do is, besides creating a new isotope, is often those less common isotopes are radioactive. So for example, carbon-12 is the most common form of carbon, 6 protons and 6 neutrons, but there's also carbon-14. That's 6 protons and 8 neutrons. Carbon-14 is radioactive. And radioactive elements in general kick out extra particles in their nucleus, whether it's protons or neutrons, in order to become more stable. In radioactivity, we say making isotopes more stable since the 1890s. Radioactivity was really discovered in the 1890s. So there's 3 main types of radioactivity. The first, which we've sort of talked about a little earlier, is called an alpha particle. An alpha particle is essentially a helium nucleus. It's 2 protons and 2 neutrons. Helium's atomic number is 2. So any radioactive element could emit an alpha particle, which is also the equivalent of a helium nucleus. It doesn't have to be helium. There doesn't have to be helium anywhere around it. Anytime a radioactive element emits a cluster of 2 protons and 2 neutrons, it becomes, that is an alpha particle. And obviously then its atomic number is going to decrease by 2, so that's going to change the element by 2. The second kind is a beta particle. So if you know your Greek alphabet, we go alpha and then beta, which for those of you who are English people out there, you enjoy English, the word alphabet comes from alpha and beta. There's several different kinds of beta particles. I'm going to highlight 2 here. The first is, if you remember, neutrons and protons are made up of smaller particles called quarks. And those have partial charges, and because of that, neutrons and protons can actually become one another by changing the number of quarks, and possibly there's some stuff left over. A neutron can become a proton, and in that case, an electron is emitted from the atom, and that electron is a beta particle. Another way that you can end up, and then obviously you have gained a proton, so your atomic number goes up 1. You can also have a proton becoming a neutron, and what's called a positron is emitted. And in that case, your atomic number would go down 1 because you've lost a proton. So there's different types of beta decay, we call it, but beta particles given off. A positron, interestingly enough, for those of you who are really interested in what's going on in nuclear reactions, a positron is actually what's considered antimatter. It's like it's an anti-electron. It's just like an electron, but anti-everything, which is a little crazy. Some of the extra credit is going to have to do with antimatter. And then the third type of radioactivity is gamma rays. And those are not particles at all. Gamma rays, as you remember from studying the electromagnetic spectrum, are the really high energy, super deadly electromagnetic waves. And in giving off certain types of radioactivity, elements can actually give off gamma rays. That's why so many of the early scientists who studied radioactivity ended up with cancer because of the gamma rays. So when we're looking at stopping radiation, a good key is the more it takes to stop the radiation, the more harmful it is. You can think of that with normal everyday objects. If you have somebody throwing a baseball at you, the more force it takes to stop it, the more harmful it's going to be to you. So an alpha particle is stopped pretty easily by a piece of paper or even a small pocket of air. They're not terribly deadly. A beta particle is stopped by several sheets of paper or a large pocket of air or a heavy metal sheet. So more dangerous than an alpha particle. However, gamma rays can really only be stopped by thick layers of lead. That's why in a nuclear bomb, which we'll talk about later, that gives off a lot of gamma rays, it doesn't really matter where you are unless you happen to be in a lead-lined room. The gamma rays are going to penetrate right through any building. Not necessarily destroying the building, but certainly going through it. One of the things that they noticed in hospitals in Hiroshima, where the first nuclear bomb was dropped, was that X-ray plates that you would develop X-rays on were exposed to radiation, and they were stored in the basement of the hospital so that no radiation could get to them. And that was one of the mysteries, was how did all this radiation, where did it come from? How did it get to these X-ray plates? And that was the gamma rays from the nuclear bomb. So then let's look at nuclear fission and nuclear fusion, and that's in chapter 20. And we can look at a couple things that we're used to are bombs. Obviously, when people think nuclear, the first thing they think is bombs, and a lot of people think nuclear means deadly or something like that, and it really just refers to the nucleus. Clean power, so nuclear power. And you remember earlier there was an article on my website, it's still there somewhere, about the difference between the uranium you need for bombs versus energy. And when we say energy, I mean like electrical energy. And then the sun. The sun is powered by nuclear fusion. So let's look first at nuclear fission. So nuclear fission is the splitting of the nucleus of an atom. And it was this guy, Szilard, and you're going to watch a video on him, who really came up with the pathway for how nuclear fission could work to really get you sizable amounts of energy. And the basic idea is that in heavy atoms, more energy is required to hold a heavy nucleus together than for the separate parts. And so in bashing, say, a plutonium nucleus in this picture apart, you get smaller atoms, you also get some extra neutrons going off, and you get extra energy. The extra neutrons can then be used to bash more plutonium nuclei apart, and so forth and so forth, and so you get what's called a chain reaction. And that's what's going on in atomic bombs like used in Hiroshima. This is also what's used in nuclear power plants, but again, the grade, the purity of uranium that's used is very different. So it's not like somebody could hijack a nuclear power plant and use it as a bomb, although if things go wrong in a nuclear power plant, it's still pretty deadly, as we've seen in recent years with the tsunami in Japan and in Chernobyl and 3 Mile Island and things like that. One of the things to keep in mind is when we talk about nuclear bombs, we're talking about the whole class of fission bombs and fusion bombs. When we say atomic bomb, we're really talking about fission bombs, and that's the only kind of bomb that's ever been used on people. And we'll see why in a minute. So besides using these because we use these heavy nuclei, all of these heavy nuclei are radioactive. So in addition to all this energy, the energy you're getting, or a lot of the energy you're getting, is in the form of high energy gamma waves and X-rays, which are incredibly harmful to people on a long term. So we're not just talking about a lot of energy to blow a lot of stuff up. We're talking about 30 and 40 years later, people are still getting cancer from the bomb you dropped, and you may now be allies with these people, as we've seen with Japan. Japan is one of our strongest allies. And yet, 20 years ago, when we were allied with them, people were still developing complications due to the bomb we had dropped in the 40s. So that's a big problem with nuclear bombs. Nuclear fusion, on the other hand, is the combining of atomic nuclei. So kind of the reverse is true here. In nuclear fusion, it takes more energy for two separate nuclei than for the combined one. And so because of that, we're usually using really small nuclei. Hydrogen is often used, which is why we call those bombs hydrogen bombs. Fusion bombs are called hydrogen bombs because they use hydrogen. And this is also what powers the stars. There's a lot of research into using energy or getting fusion power plants. One of the hardest things is that it's so hard to contain. There's so much energy produced in nuclear fusion that you end up melting down your plant with the energy you're generating. But the pro to nuclear fusion is because you're using things like hydrogen, these aren't big radioactive elements. They're not radioactive at all. And so while you're getting a lot of energy, you don't have the gamma rays and the X-rays that are so harmful. One of the things that, if you're interested in looking at, it talks about in your book, is why in the nuclear reactions mass can be converted into energy. And so remember, we've talked about this, there's only conservation of mass in physical and chemical changes, but not in nuclear changes. Although most of the mass is conserved, some is converted to energy. So that's discussed a little in your book. The other thing that some people, those of you who like the bomb side of these, might find interesting is that hydrogen bombs, besides being so deadly simply because they produce so much energy, most hydrogen bombs are enclosed in atomic bomb shells. So because there's no radioactive particles in a hydrogen bomb, what defense departments do is they enclose them in atomic bomb, almost like atomic bomb linings, so that as the hydrogen bomb blows, you get all of that energy, plus that triggers the atomic bomb to blow, and so you also get the radioactivity that's so deadly for so many years. So that's why hydrogen bombs are really kind of, especially in the 80s, they were the real scary thing. Sort of what terrorism is now is what hydrogen bombs were in the 1980s, because, I mean, imagine the amount of power behind that. Hydrogen bombs have never, by the way, been used on a human population. So that tells you a little bit about radioactivity and nuclear fission and fusion. Please don't hesitate to put any questions on the website.